Everyone. I'd like to introduce Wes Wilson, talking about how to use machine learning to make life better for people. So, over to Wes.
Yeah, good. That's a good title introduction. Thank you very much. So welcome. I'd like to thank everyone all the volunteers and organizers of DDDPerth putting on this amazing event. And I'll thank all you guys for voting for my talk. Hopefully you find it interesting. I wasn't sure if brain tumors got everyone as excited as they get me excited. So here we go. And of course, thank you to all the sponsors who put on this event to allow us to speak here for fairly cheap. So about 12 years ago, a 12-year-old boy came into a clinic in Markham, Ontario, Canada, which is my hometown, pictured here. Small little town, little hockey town. Ice hockey, real hockey. And he came into the clinic and he had a 10 out of 10 headache, the worst headache you can imagine. And he was vomiting, but he had no nausea at all. And physicians are trained to treat this as a brain bleed until proven otherwise. So it's very serious. We get the CT image of his brain, but there's no bleed. Instead, there's a brain tumor the size of a golf ball in his fourth ventricle of his brain. It's secreting cerebral spinal fluid, which is causing an increased intracranial pressure, causing a medical emergency. He's sent down to the closest city, to Toronto, at the Hospital for Sick Children, where emergency surgery is done in order to save his life. At the Hospital for Sick Children is where I first started and got into pediatric neuro-oncology. Brain tumors in children are the #1 cause of cancer-related death in children worldwide. And this fact is staggering once you realize that it is a rare cancer. Childhood leukemias make up the vast majority of all cancers, but not even close to the amount of deaths from brain tumors. Now, there's lots of kinds of brain tumors. These aren't a homogeneous set of diseases, many subtypes. And they're all various degrees of aggressiveness. They respond differently to different treatments. Some can be surgically resected, some can't. For example, the type of medulloblastoma, known as a Wnt-type blastoma, has a malfunction in one of its pathways. And this causes a side effect that the blood-brain barrier gets disrupted. Now, this is actually advantageous for children with the Wnt-type medulloblastoma, because what this means is that the compromised blood-brain barrier actually allows more chemotherapy agents to cross the blood-brain barrier and get to the tumors, which is why Wnt tumors have a better prognosis in children than, let's say, group 3, which is of the same class of medulloblastoma. So different types of treatments, very different tumors, subtypes are important. That's the key take-home from that one. So how do we tell the difference between these types of tumors? Well, for some cancers, let's say you had skin cancer, melanoma, or breast cancer, it can be very obvious. You can look at it under a microscope. They have different morphologies. They look very different. But for brain tumors, this can be problematic. Medulloblastoma, under the microscope, looks identical to pineoblastoma. You can't tell the difference. Traditionally, the way these tumors have been distinguished has been, where are they in the brain? So if you had a tumor growing on the pineal gland, which is pictured here, I don't expect everyone to have perfect neuroanatomy. Mine's not great. Everything looks the same to me. Then they'd say, oh, it's on the pineal gland. It's a pineoblastoma. But this can be a problematic way to diagnose brain tumors. For example, this image here, taken from the UCLA neurosurgery page, from the pineoblastoma page, is a great resource of information for patients. But there's a little subcaption under this image that says, after they've resected the tumor and analyzed it, it ended up actually being a glioblastoma. It wasn't a pineoblastoma at all. So how do we diagnose the subtypes? How do we figure out which treatments are going to work? Well, there's 2 groups in the world that kind of do it the best. There's one in New York, and one in Heidelberg, Germany. Now, most people use Germany. It is the gold standard. It's the one that they do it the best. They have the most robust algorithm. It's the secret, but it's considered the best. So a patient comes into Perth, the Perth Children's Hospital, with a brain tumor. We cut out a biopsy, freeze it, send it to Heidelberg. Heidelberg then runs some tests on it. They use what's called a DNA methylation array. DNA methylation, you might have heard about it. Epigenetics is a big buzzword these days, turning genes on and off. But it can also act as just a fingerprint in your genome, which can be associated with different types of tumors. And they have a black box algorithm that can look at this profile, tell you what it is. So once they finish analyzing it, they write up a report. They look at the histology as well. They get a little slice. And they send that back to Perth, where we were like, okay, this is what the patient has. Now, this can be problematic because that can take time. And sometimes you have to start treatment before a couple weeks pass when you get this diagnosis. And if you have to start treatment before you know what the tumor is, why even bother diagnosing it? If it's not going to affect your treatment plan, it doesn't change anything. Now, for other nations that maybe are closer to Germany, there are other problems that this presents as well. One is cost. Not every country can afford to ship samples to Germany and back. Now, Perth Children's Hospital, just so you guys know, does have a special deal with Heidelberg. We get to ship our samples for free. In exchange, they get to keep the patient data, and they build their algorithm to make it better and better. So we're trading our data for free analysis. Not every country can do this, however. Some countries have laws that prohibit black box diagnosis. So like Sweden, for example, they can't use Heidelberg, even though they're close by. The system, their healthcare system does not allow them to be like, here, take these medications. I can't tell you why. You can understand that can be an issue as well. So I always find myself sort of teetering here between, I've been a developer for the last 20 years. I've also been in oncology for the last 8. And there's always this little sliver, I consider myself, also an ice hockey player a little bit of my time. And I think like many of you in here who are technologists, who are developers, engineers, we look at problems differently, right? We kind of look at them and we're like, how can we solve it? And so a colleague of mine, Dr. Melvin Chin, who sits beside me, pictured here thinking, please don't put me in your PowerPoint. He calls me a solutionist. He says that I go and I solve problems just for the sake of solving them, even when the problem's not that bad, but the solution takes so much longer than the problem would have caused me to begin with. And he's not entirely wrong. But sometimes, in my past, I have hit some healthcare problems, solved it with technology, and been able to leave those projects behind with a solution that other people can solve. So obviously, this time around, I'm like, all right, there's got to be a technological solution. There's something we can do to solve this problem. And I wasn't alone this time. There was a group in Sweden who I brought up that they have the issue that they're not allowed to use Heidelberg. Here in Perth, I'm concerned for the time. So a group led by Helena Krellen, who has a brain tumor group in Gothenburg, Sweden, and one of her postdocs, Mohammed, we set out to try to solve this. And it had to accomplish 3 tasks. The first is it had to be cheap. It had to be cheaper than sending your samples to Heidelberg. It had to be affordable enough that a hospital's budget wasn't going to break by implementing this. It had to be easy. Pathologists aren't going to have the ability to take on bioinformatics skills. They're not going to have the budgets in the pathology department to hire additional expertise. And lastly, it had to be accurate. We knew going in, there was no way we're going to develop something as robust as the Heidelberg algorithm. We knew we weren't going to be able to afford to spin up 200 cores and run neural networks on training sets. It was not going to happen. But if the output, if the result was just as accurate or better, then it doesn't matter. So first, we started by collecting samples from the Gene Expression Omnibus. This is just this online repository of all this genetic information. There's RNA arrays, DNA analysis, SNP data, and also DNA methylation array data. So Mohammed went through it all, cleaned it up, got some missing values, and at the end of the day was able to find 472 pediatric brain tumor samples in the database. Of that, 9 of those had 9 different tumor subclasses. Then using basic kind of linear regression modeling, ROC curves, we cut down those 450K arrays, which has 450,000 probes, to a 900 probe pool that we were able then to make fingerprints out of. And that became our training data set. Those 472 tumors from a 900 probe pool became what we used. And we decided to make a multi-class random forest algorithm. And so this part, I'm going to get a little bit more in the details, just so if anyone's interested, especially if you're new to modeling, maybe you can take something out of this and say, hey, I learned a cool thing today. So the training set is our 900 probes. And from that, we break out into classifiers, the n number of classifiers. Each tumor subtype has multiple classifiers, not just one. Then you take the DNA methylation data from your unknown tumor, from your patient. You run this through all the classifiers. It's going to match each one to a various percentage. If it's really a pineoblastoma, it's only going to match to a medullary fingerprint by like 19%. But if it matches really tight with a pineo at 93, that's a better match. Then you add all all those classifiers up at the end, and you get a prediction with a certain percent confidence interval of what the tumor is. Now, this whole thing is done through random forests. Now, if you're not familiar with random forests, some of you might be, some of you might not be, it's a way of removing instability from regression trees. So if anyone's ever played with any kind of regression trees or just seen them in general flowcharts, that first branch, right, that first one we decide which way to go, can be critical because there's all these downstream branches. But that first division can change how everything ends up. And that first division is really sensitive to your training set. If your data is a little different when you start, that first division can be different. You might get a different answer. So what a random forest does is it takes your data set, your training set, randomly deletes 1/3 of it, generates a tree. Randomly delete another 1/3, tree, another third, tree, until you have a whole bunch of trees and you have a forest, and that is random forest. And so we run this tumor data through the forest, then add up all that at the end, and that removes that instability that's inherent to regression trees. And we call this whole system METHPED, methylation pediatric neuro. So, nice little package, a nice little setup, we kind of like it. And this solves that first one, cost. This is a very cheap algorithm to run once the hard work is done. You can run it on your work computer, MacBook Pro, Acer, it doesn't matter. You don't need a lot of cores. It's cheap. But not very easy to use. So the last year on my weekends and some spare time, because I actually do lung cancer work normally for my day job, this is just a side hustle, as it were. I've been working to try to make this more easier for pathologists to use. So I start with methylation data that you get right from the machine, from the DNA methylation arrays. Normally, you put this into Genome Studio. This is what we did for the first training set data. But this is a clunky piece of software. People hate it. Even bioinformaticians get in, normalize the data, get out, do it in RTAP, do it in R, get out of this thing as fast as you can. Pathologists were not going to want to open this up and be juggling different software packages. Luckily, the solution to this was solved many years ago by Hansen in 2011. He reverse engineered the Illumina normalization set. And so I built his algorithm into our software. And then I pre-bundled all the manifest data that tells the array what's on the chip, where all the probes are. This is something we just did because we didn't want the software to have to connect to the internet. We didn't want some pathology departments, a lot of computers in hospitals can't just connect through an open API. There's a lot of ports that are blocked, a lot of patient data that's sensitive. So we bundled all those manifests in. Then we use an open package called Minify, which is open on Bioconductor. It just has a bunch of tools that allow you to manipulate DNA methylation data really easily. And I use that to then calculate these intensity differences values. And then, because we're all kind of like dirty hackers, I just toss that junk into like a matrix and then shove that matrix into METHPED. And then this whole process, this pipeline, I call this MethylDX. I'm not committed to the name yet. If you guys have better ideas, come bug me at lunch. Maybe something with a pun in it would be really good. I like puns. This can be run on any computer. It's really simple. You just literally drag the intensity data file from the array onto this, and it spits out a diagnosis with a confidence interval. So now we have the first two. We have it's cheap, now it's easy to use, but is it accurate? Because if it's giving you the wrong diagnosis, it's pretty much useless. And so this comes to our validation step. And this might be one cool thing you guys can take away from this talk. If you're not familiar with the tripodstatement.org and you're doing any kind of modeling at all, rarely recommend that you check this out. This is being really pushed hard by Andrew Decker, if you're familiar with his work in modeling. It's one of his pet projects. Basically, there's types of validation steps, one being like the least valid, type 4 studies being the most valid. I'll let you go to the website and read it all. I won't go through this flowchart. But basically, we were only able to do on ours a type 2. And we didn't have access to a lot of tumors. As I previously mentioned, brain tumors are actually quite rare. And so what Helena was doing with her team in Sweden was she was reaching out to all her physician friends all across Europe and trying to get more pediatric brain tumor patients. And so she was doing that for the last year while I was doing the MethylDX for the last year in the project. But then I accidentally stumbled onto something. So my former boss at Telephone Kids, who's now at Perth Children's Hospital, Nick Furtado, over his career, he's had, 15 or 16 brain tumor patients. 12 of those, he sent samples to Heidelberg. They were not in the original Gene Omnibus training data set, and he just had that data. So I was able to take Perth's isolation, being so separate from the rest of the world, and use that to validate our study and jump ahead and conduct a type 4 validation study. Now, I'm not going to get into some of the crazy maths involved, the statistics of comparing data sets back and forth, but I'll just talk to you a little quickly about what the results kind of were and some interesting issues with comparing data sets, comparing results. And maybe we can talk about this more. Legend wants to talk to me, especially people who have a more statistical background in this kind of thing, so I'd love to hear about it. So we get our 12 tumors. And one thing to understand is that the official end game diagnosis, one thing that's written in the charts, is whatever Path West says it is. So they became the gold standard for what I was going to compare back to. Now, Path West has access to patient history, family history of types of cancer. They know, they have blood tests, they have CT scans, they have the biopsy, the histology, the pathology. They have access to all the data you can imagine to make the final decision. So the doctors do send those samples to Heidelberg. Heidelberg only gets two things. One, a sample of the histology, and they get to run the methylation data array. They don't get all the other scans. But Path West does get Heidelberg's report back. And that's where this gets a little muddy in the water. Path West makes the final decision after reading what Heidelberg thinks it is. So take that with a grain of salt. When you compare Heidelberg with what Path West finally decided, Heidelberg agreed with Path West 10 out of 12 times. So 83% of the time, Heidelberg is getting it right in the eyes of Path West. When you compare that to MethPed, our algorithm, it's a little bit different, but it's still kind of interesting. So for the first tumor, for example, tumor number 1, Heidelberg got it wrong. But MethPed got it right. Yay! Unfortunately, for tumor number 10, Heidelberg got it right. MethPed got it wrong. Ooh. Well, an interesting thing that came out of it was this tumor here, tumor number 4. Tumor number 4 was a really weird-looking tumor. It was sort of a hybrid of other kinds of tumors and looked like a mixture. And Heidelberg confidently said, I know what that is. Here's what it is. Path West experts were like, nah, you're out the lunch, you're crazy. Meanwhile, the way I tweaked the confidence intervals, how I said MethPed should agree to tell me what something is, and how confident it was for this validation study, was set to a way where it said, it looks like this tumor kind of like 36% of the, matches 36%. It kind of looks like this other tumor, like 28%. But I'm not sure. I'm not going to tell you what it is because I'm not confident enough to make a prediction. And it said, all right. So in that respect, I think that's a promise, a good mark for MethPed. And remember, MethPed only has the DNA methylation data. It doesn't have histology. These predictions are purely unbiased on the data set. There's no human bias added by looking down the scope, which could be pros or cons. And that's something I think we could maybe discuss if I want to chat more on lunch. Because I am sort of just running out of time. But like I said, if anyone wants to chat with me about machine learning, about algorithms, about cancer, I love to chat about it. Please do come find me because I can talk about it forever. We can grab a drink at a little party and hang out and talk more. I do want to thank Palsy Supercomputing for providing some support for this project, the Australian government, and my actual where I work, the National Centre for Asbestos-Related Diseases, for giving me the time and encouraging me to pursue these side projects in cancer and letting me come here to speak with you guys today and give me the time off. So thank you guys.
We have a few minutes for questions. Does anyone have any questions for Wes? The question was, how do you use the supercomputer at Palsy?
Physically, I SSH in, but I think what you mean is, what are we doing with right, so the actual validation steps, so comparing the stats and comparing a lot of the values and the p-values and the r-values and the r-squareds and determining, we use a mixed model analysis to figure out how good we are predicting these models. That validation math, we're doing that on Magnus. We didn't use XGBoost, but you know what we did try? We tried like an SVN at one point, but the tweaking method, going back and forth, it sounds like you know what you're talking about. So when we go back from our training set back to our output, right, and then you go back to your training set and you keep going to get the right values, and you keep tweaking the numbers, the spaces between the bars and the SVN became so picky that we ended up massively overfitting. And we were like, this is not the approach here for us. Yeah. Yeah, that was sort of, based on literature and some other models, we kind of homebrewed our own sort of script to bring them back together and calculate the values back together. We didn't use the library for that.
Time for one more. If anyone's got any questions.
It's a great mix, and that's kind of thing. One of the reasons why we kept doing it, even though it's all volunteer work, is because it's a lot of fun. It's for a good cause, but it's also fun. So a lot of the methylation data manipulation is done in R. A lot of the front end stuff is done in Java because we wanted to be multi-platform, which is an easier way for us to do that, and what I was familiar with from doing Android apps anyway. And then with some of the server-side stuff is Python. So one of the things we're trying to do, if we can find a host, is I want to push out a beta of it online. If I can find some of the hosts for free, just to get people interested. And pathologists interested in playing with it. Because it can be, one of the barriers to access is getting into all the hospitals and get people to approve to run the software. And if we can get pathologists to play with it, like it, then they can make the pitch to their hospitals that, hey, we should use it.
Thanks again, Wes.